So what I'm trying to do today is learn more about the chain rule and the backpropagation. Because that's what we kind of got stuck last time, right? So we got stuck with the fact that we have the differential stuff that's computed from the outcome, but then we want to modify, so we want to create something that modifies W2, right? And then we move forward. So we want to learn more about the chain rule and then how that maps to backpropagation uh, in machine learning. If I remember well, the chain rule, right, is something like it's derivation rule, right? Something like that if you've got a function of a function or something like that, the derivative is the derivative of that function times there's sort of like a chain rule in terms of how you compute the derivative of something that is a function of something else or something like this. Um, in this case, because we've got like a forward pass that basically is made of W2, W1, and W2. Not only that, it's like it's made of a Z1 that's like the dot product between X and W1 plus this bias, and then there's still this activation stuff in here going on. So the whole thing is a huge, yeah, and then kind of like Z2 and ultimately Y, the output, is basically a function of a function, right? Because it's a dot product between A1 and W2. And A1 is basically that nested thing here. So let's just ask Ghost, right? It's like let's try to learn that a bit more in an isolated way first. See, maybe we just have to make another test like file. But I'll ask Ghostwriter. I want to learn. I want to learn about the chain rule and backpropagate and how it relates to backpropagation and machine and neural networks. Can you guide me with a bit of theory and a practical Python example I can follow interactively? Okay, so so it starts with, okay, so let's see. Um, let's create a file. It's just going to be like a prop.py. Oh, sorry. What am I doing? I actually want to. I wanted to create a file, right? And I want to use this file. Okay, so what have we done here? So a simple fit for neural network with an input layer, a hidden layer, and an output layer, and see how we would apply the chain rule and backpropagation. So now by a sigma derivative. Okay, so we actually have the derivative in here of sigma. Initializing the data, initializing the output data. One. Initializing the weights 1, weights 2, number of iterations. And so forward paths. Layer 1, layer 2. So here's the same thing. Layer 2 error is y minus layer 2. And then, okay, so here we're getting something completely. So we're getting layer 2 error times the sigma derivative. And then this delta, sigma derivative layer 2. There's a lot to unpack here. Compute how much layer 1 contribute to the error in layer 2. So then we do layer 1 error, layer 2 delta. So in a way, that's kind of computing what's layer 2 delta. So what would layer 2 would have had to be, so there's a layer 2 error, which is y minus layer 2. Then there's layer 2 delta, which is the error times the derivative. The derivative with respect to layer 2. Oh. Ooh, 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 ooh. I'm passing x in here. What does this even mean? It's the sigmoid of something. Is like, okay, sigmoid. I guess this just broadcasts to each element. Sigmoid derivative. I guess that casts because NP dot is not probably an x and weights one, right? So that's kind of the equivalent of our A1 element, and that's then uh, layer 1 times layer 2, and that's kind of like, yeah, that's layer 2, so that's the output actually. Weights 2 is W2, right? So we're literally computing the delta. This is what would layer 2 have had to be in order to obtain, because that's otherwise wouldn't make sense, right? So it's supposed to be what layer 2 would have had to be in order to have zero error. And then we compute layer 1 error based off of layer 2 delta. No, it's the delta. This is definitely, this needs to be done packing. Like updating the weights is okay, right? But then we obviously have something that layer that makes sense. Like that we are updating weights 2 and weights 1. That's what makes sense. Okay. Is it about fee for an hour with an input layer, hidden layer, and output layer? The backpropagation is done using the chain rule, which is representing the code by layer 2 delta, layer 1 delta variables. This represents the variable, the derivative of the error with respect to the weights. These are computed by propagating the error back from the output layer to the. Okay, but how is that propagation? So can you so we need to explain. Can you explain the theory behind behind this line? So this line is implementing the backpropagation step in a neural network. Backpropagation is how neural networks learn by adjusting their weights. And layer 2 error is the difference between the predicted output of the network and the actual design output. This error is propagated backwards to adjust the weights on a network. Okay, sigmoid, this we know. Sigmoid derivative layer 2 function gives the derivative of the sigmoid function at the values in layer 2. When you're doing backpropagation, you compute the derivative of the activation function to decide how much to change the weights and biases. Yes, because well, you so that this is what I think this is what has been confusing me all the time here. When we do that, when we do not even in test, but like whatever, when we're doing these, we're calculating the error. We're not calculating. It's not the derivative. Like if I actually open, if I open I open, is it train? Or is it neural network? It's neural network. I open neural network. That's the problem. See, the problem is that I just know like you're not multiplying by any derivative or anything whatsoever. Like we're calculating an error. And that's all we're doing. And so what we're doing here is we're saying calculating the, so we have the error. Sigma derivative 2, derivative so layer 2 is basically saying we have our, so we have our cost function. We want to minimize and optimize that cost function. This means that if we calculate the derivative, right? The derivative tells you how much and in what direction you have to change things. So the layer 2 delta is essentially calculating the amount to adjust the way it's connected to layer 2. It's computed by multiplying the error, how wrong we were, with the derivative of the sigmoid function. How sensitive is our network to changes at this point? Okay. So why is multiplying the error by derivative a good choice? Gravity of error. By multiplying the computed error with the derivative, we ensure that the larger the error, the larger the adjustment is made. Learning from wrong predictions in situations where our network confidently made a wrong prediction, the derivative of the sigma function will be larger. Confident mistakes. Okay, so in a way, it's amplifying. I know. Okay, that's actually it's interesting. So in a way, it's just basically you're saying, well, you have the derivative function. You have the derivative, and then you want to amplify the mistakes. Yeah. The correction of the mistakes, but still in this example, sorry, it's not here, it's actually here, up here. Still in this example, so what is it that we have here? In this example, this is also just has the shape of layer 2. Okay, but we're multiplying, so we're multiplying this error times the sigmoid. With respect to layer 2 is basically something that is just a dot product, right? It's just so these two should have the same shape. Sigmoid derivative. That is the so okay. So we have the sigmoid derivative, but then we want to multiply it by the actual error because sigmoid derivative. Um, the, the derivative is going to tell you at any given point, like let's say if you've got a, like if you have, uh, that's what I want. Okay, yeah, exactly. So if you have, can I click canvas confirm? If I have something, so it works like these, right? The derivative of this function is going to be something like these, so to say. Not exactly, but yeah, right? Is it? Yeah, whatever. Something like these. Um, so essentially, to minimize, like if I evaluate it at this point, it's going to tell me, it's going to give me a number and I know where to go, right? I know I have to go minus. Um, I'm giving it layer 2 as an input, the sigma derivative. But here it's the, wait a second, wait a second. So here we're using the derivative of the sigma function, which is the forward pass function. It's an activation function. Where is here the cost function? Okay, so in the example you gave me, both in C, sigmoid is used as an activation function, which in our case was tangent, like tan h, and then the derivative is used to compute the changes. Where does the loss function come into play in your example? Because I thought that you're doing this with a loss function, because that's what you're trying to minimize, not the activation. Is implicitly used. Here, the difference between the network's prediction and the actual target is simply calculated as. Oh, okay. This corresponds to the mean squared error loss function. This is commonly used for regression problems. For binary classification problems, where the output is either 0 or 1, the MSA loss function simplifies to be the same as the difference between the actual and predicted when only a single prediction is considered, as in this case. Generally, in more complicated examples, specifically when using different activation functions or while working on multi-class classification problems, you would explicitly use a loss function like cross-entropy loss, often paired with a softmax activation function for the upper layer. Bro, that's what I'm doing. Okay, and then the derivative or gradient of this loss function will be used in the backpropagation process. Often paired with softmax activation function. But in this basic example, okay, so we're kind of peeling off some of the layers here. That's good. So this means when we're doing this is a very simple way. It's like you're just looking at the error. That is actually your cost function. Your cost function is you're just doing the mean squared error. So what I was doing before is definitely wrong. Now, if you're using something else, like cross entropy loss, then you would use that to actually measure the loss and not just the minus thing. But now this raises up another question, which is, is it in general, or is there, that's the pairing choice between activation function and loss function matter? Let's think about it for a second. The activation function is to add this non-linearity thing in there, right? Why would it? Why would this matter? Why would this matter at all? I don't think. I would assume this is nothing like the loss function versus the activation function are totally unrelated. Yes, okay. The choice of pairing between activation function and loss function does matter. Certain types of loss functions work better with specific types of activation functions, especially for the output layer. Here's some common pairings: binary cross entropy loss with sigmoid, categorical cross entropy loss with softmax. The solid activation function squashes the outputs for each class between 0 and 1. It's up to 1. That's interpreting those probabilities. The categorical cross true class probabilities. Okay. In what sense does it matter, though? In sense that are, you know, so that these combinations work optimally because the derivative of the loss function with regards to the raw output from the last layer, which is needed for the operation, can be computed in terms of just the predicted probabilities. The true values simplifies calculations and also avoids numerical stability issues. Okay, wait a second. These combinations work optimally because the derivative of the loss function with regards to the raw output from the last layer, which is needed for backpropagation, can be computed in terms of just the prediction probabilities and the true value. Yeah, but that's nothing to do with the choice of the activation function per se. It's just how you design the. Obviously, you have to use a loss function that can work well with the output type. Okay. Maybe I'll ask that on X. See what X has to say about this. X.com. See what X has to. Let's see what other people have to say about this. Ghostwriter says that, but let's see. So, okay, so this means, let's see, what does this mean? What does this mean? This means that we're doing stuff wrong, right? Well, this means here there's an implicit loss function, which is just basically the error. And but still, you're multiplying by the derivative. Oh, sigma function is a bit odd. It's very odd. I don't understand. I don't understand why. I don't understand why. Mm, it's the activation function. The activation function has nothing to do with the loss function. It's nothing to do with the loss function. No. The loss function is just the error, right? Uh, the loss function is just the error. Um, like for me, this would mean the following. So for me, for our toy example, for our toy example, for our toy example, this would mean well, it means we need to actually have the it means give me a second, let's okay, back online. Actually, okay, let me so it makes sense in a way. It makes it makes sense of using A1 because that is the activation function. So what is the derivative of these? And I'll just be that as the fact. So, okay. Gradient function. Another plus. One is square gradient function. This derivative is used when computing gradients of operations. But that's missing here, right? That is definitely that is actually what's missing. These are two. So forward pass. So here we're creating the difference. Then we're calculating dw2, and that's kind of done in the wrong way because is transposing a1. It should multiply these. Uh, that's wrong. It should multiply. It should do a dot. It should do a multiplication of the derivative of these times the derivative of these. All right, assuming I'm kind of like basing it off of the example that we just saw, where we're saying cool we're using the mean squared error or whatever, so we're just using that thing here. Um, you know what? Actually, a quick test that we can make. Let me try that. It's totally unrelated, but I just kind of realized maybe I should be like I start to understand like I think where these things are. There's still one thing I don't understand is like why are we using the activation function? Why are we deriving the activation the derivative of the activation function? This I just don't yet understand why this makes sense. Um, but if we take that as a truth, if we take that as a truth, and kind of we go open our neural network, our train file, okay? So remember, with the train file, what we're doing is we're doing this kind of training, blah, 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 blah. We have this loss function here. That's kind of what that's instead of these, right? It should just be the minus thing that we're computing. Um, although, okay, give me a second, guys. I'll probably have to. I just have to do that in a second session. But I think that's. I understand. Actually, no. What I just was gonna do makes no sense anyway because now I truly understand what's happening here, which is like with this loss function. This loss function is designed to kind of calculate exactly like in a way it's implicit, right? Because you know that the y true index is true, and then you want to take a look at these, and then obviously that logarithm is going to tell you how like it's a measure of a difference between these. So obviously it doesn't take into account which one you flagged as wrong. It just takes out what was supposed to be true and then what's the actual predicted value. And that is essentially, obviously, the same as kind of minusing. It's the same what you're doing, is kind of minusing, right? But instead of even minusing it, like I believe we should be using these instead of just the minus. This is also what because then what I was doing here in the test file of that one's going to be -1, one's going to be 1 makes no sense at all. Like we should just be actually using exactly the same thing. So we should just look at the predicted versus the predicted truth versus what's the actual true versus the predicted, uh, and we should ignore these. It should just be, but still it doesn't kind of work, right? Um, Maybe the one thing I can indeed test here is but I don't know how to do this though, because I'd have to fix a lot of the stuff because I think it's not working well with reshapings and whatnot. But I think in the so blah 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 loss function backward propagation. I think what we should be doing is yeah, I think we should change the way the backpropagation works. I think definitely there's missing here to do. So are we missing multiplying by derivative of tan x? The activation function. Why? Why do we need to multiply this by the activation function? I don't know. But that's kind of what the example is suggesting. Now I understand these, but then here we should just not use that. Just use the actual. Use the actual loss function. Use the actual loss function. I don't even know. I don't even know if that was the initial suggestion even at all. You know what I mean? I think that was even. I don't think it was just like a minus. Like, get a single integer. I think that's because I have a feeling I kind of somehow modified that. I would have to go and check the history of the file, but I believe that originally was something like that. So I actually have to just use that. Yeah, that's actually the loss function. Just to know why I have to multiply. Okay, that's my next. We're going from question to question. That's kind of the next question. Why do I have to multiply by the derivative um of the activation function at all? Uh, and then still finalize to understand the rest. Okay, see you in the next video then.